Okay, this is the lesson video for section 2.3 on continuity for AP Calculus AB. And before we jump into this today, I just want to give you kind of a brief overview. When we talk about continuity, this is actually a topic that a lot of you will probably just consider to be common sense. When you look at a graph, it's usually pretty obvious whether or not the graph is continuous or the function is continuous on some interval. But we have a mathematical definition that we have to use to define what continuity is. And so that's the main thing. So we've got really kind of two key topics we're going to talk about here. The whole idea of how do we define continuity mathematically. And then as an extension of that, we're going to get into something called the intermediate value theorem. So those will be the two most important things that we discuss here. And what you'll find is continuity is fairly simple, but a lot of things with the way that you word your statements when it comes to continuity, that can make this just a little bit tricky. So you've got to really pay close attention to the way things are phrased when you're looking at where a function is continuous. Okay, so to start with, like I mentioned, you can usually tell if a function is continuous just by looking at it. And a real simple explanation of that is if you can graph that function without lifting your pencil, then we would obviously say it's a continuous function. Now, here's the key though. If we want to describe that mathematically, so the correct mathematical terminology to describe continuity, well, we can describe continuity at a point in this way. In order for a function to be continuous at some point, the limit value at that point has to equal the function value at that point. And so that's what's going to determine our continuity. And if we want to talk about continuity on an interval, then we would say this statement holds true for any point within that interval. Okay, so here are some examples of graphs that are not continuous. Now, notice they all look somewhat similar, but they're not continuous for different reasons. And so now, rather than just looking at the graph and being able to say, okay, well, I know it's not continuous, now you have a way to mathematically explain why is this not continuous? Because remember, the limit value has to equal the function value at a point in order for the function to be continuous. So let's just go through these one at a time. On the first one, like it says here, there's no function value defined at C. So this function is not continuous at C. For the second one, you can see that our left-hand limit and our right-hand limit are not matching up there. So our limit value actually doesn't exist at C. So again, it's not continuous because the limit value doesn't equal the function value. And then for the third one, you can see where our limit value would be. We're approaching the same point. However, our actual function value here doesn't match up with the limit value. So again, it's an easy way to describe. If you want to state that something is continuous, show that the limit value is equal to the function value. If you want to show that it's not continuous, show that the limit value is not equal to the function value. It's pretty simple. Okay, so what I want you to do here for a second is just think about the continuity of this graph. So I want you to pause the video and I want you to go through where you think this function is continuous. Okay, so now that you've had a chance to look through this, when it says discuss the continuity, what I really want to do here is I want to talk about on what intervals is this graph continuous. Okay, so it's pretty obvious between 0 and 1 that this is a continuous function. Where this gets a little tricky, and I did this without telling you first because I wanted you to think about it a little bit, where it's tricky is the function continuous at 0? And the answer is yes, it actually is. So our first interval where this function would be continuous would be from 0 to 1. And you can see at 1, it's pretty obvious the function's not continuous because we've got this jump discontinuity in our graph. Okay, so now from 1 out to 2, again, it's obvious it's not continuous at 2 because our point at 2, our function value at 2 is not matching up with the limit value at 2. So I've got an open interval here. And remember interval notation, which is what I'm using here. This is the most common notation I like to use to represent intervals. So when you have a bracket, that means you're including that point. When you have the parenthesis, that means you're not including that point. Okay, so now over here, once I get to the right of 2, let's just take a look at the graph here. To the right of 2, we already said it's not continuous at 2. So I know I'm going to start at 2. And now looking at the endpoint there, again, that's a little tricky. But over there at the endpoint of 4, we're actually going to include the point at 4. And you might be thinking with the endpoints, well, the limit value at the endpoint actually doesn't exist, right? Because at the endpoint, in order for the limit to exist, the left-hand limit has to equal the right-hand limit. At the endpoint, there is no left-hand limit when I'm at the left endpoint, or at the right endpoint, there is no right-hand limit. So technically, the limit at 0 doesn't exist, the limit at 4 doesn't exist. However, there's a special rule that applies at an endpoint, and that is at endpoints, we only look at the one-sided limit. Meaning at 0, we would just be looking at the right side limit. At x is 4, we would be looking at the left side limit. And that's how we determine continuity at endpoints. Okay, so here's just some kind of basic terminology that we're going to use. So when we say a function is continuous on an open interval, that means that the function is continuous at every point within that interval. And we could also say continuous on a closed interval, and then it would still be continuous on every point within the interval and at the endpoints. When we say a function is continuous at a left endpoint or a right endpoint, this is what I was talking about with that graph above. So when we're at endpoints, we have this special rule. We only look at the one-sided limit. Typically, we have to look at the limit overall, but at endpoints, like I said, we've got a special case. Okay, now here's where this gets a little bit tricky with the phrasing of your statements. It says a continuous function is one that is continuous at every point of its domain. And the key to this phrase is this part right here where it says every point of its domain. So we can define the domain of a function to be whatever we want it to be. And that allows us to create a continuous function when it may not appear to be a continuous function. So what I mean by that is like what's shown on this next one. It says y equals 1 over x is considered to be a continuous function. And why is that true? Well, you should know what y equals 1 over x looks like. If you need to graph it on your calculator, go ahead and do that. But clearly there's a vertical asymptote at x is equal to 0. So if I say this is a continuous function, just looking at the graph, you know it's not continuous at 0. So what I'm implying by saying that this is a continuous function is I'm implying that x equals 0 is not part of the domain of my function. I'm implying a domain restriction. So you've got to be really careful with the wording. If I say a function is continuous and you see points where it's clearly not, that means I've eliminated those points from the domain. Okay, so be careful with that. All right, a lot of the problems that you're going to see just to test your understanding of continuity, they're going to be these types of questions. So first of all, let's look at this function. It says this function is continuous. Well, if I say f of x is x squared minus 1 over x minus 1, think about what type of feature there would be in the graph for that function. Okay, and you should be thinking about a removable discontinuity or a hole in the graph. So clearly that function's not continuous everywhere. So if I say that function is continuous, what I'm telling you is that x cannot be equal to 1, or x equals 1 has been eliminated from the domain of that function. Okay, so one of the types of questions that you're going to see is they're going to say rewrite this function so that it's continuous everywhere. Well, this function was not continuous at 1. So what we need to do is we need to force our function to have a limit value equal to the function value at 1. And this is the way that it's done. We can create a new function that is still x squared minus 1 over x minus 1 for all values of x not equal to 1. But remember, at 1, we had an issue there, and there was a hole in the graph. So what we need to do is we need to fill in that hole in the graph so that the limit value will equal the function value at that point. And the way we do that is we just take the limit of x squared minus 1 over x minus 1. We take the limit of that as x approaches 1. And you would see that that limit is equal to 2. And then we just go through and we define, okay, well, at x is 1, we're going to define the function value of 2. And now we've taken a graph that had a hole in it. We filled in that hole, and now we've created a function that is continuous everywhere. Okay, so on this next page, you see that we are just talking about some types of discontinuities. And there's 4 different types. 3 of them you're already familiar with. The first one here is a jump discontinuity, which is just going to look, something like this is an example of a jump discontinuity. Absolute value of x over x. We've seen this graph. So, this graph looks something kind of like this. And obviously there's a discontinuity at 0, and you can see the graph is jumping from one value to another at 0. An infinite discontinuity is the same thing as a vertical asymptote. So those are sort of interchangeable terms. So 1 over x squared, you can see that that would have a vertical asymptote at x is equal to 0. So that's an infinite discontinuity. I'm going to skip to the third one here. So the third one says removable discontinuity. And a removable discontinuity is just a hole in the graph. And we saw one of those just a second ago. So hole in the graph is another terminology or another term for a removable discontinuity. So the last one here that we didn't talk about yet is the oscillating discontinuity, and that's the one that might be new to you. So an oscillating discontinuity, I'm going to show you graphically what that means because it's a little bit different. It's actually kind of obvious that it's not continuous right away, but I'm going to show you on my calculator what this looks like. So this is the sine of 1 over x. And if you want to, you can graph this on your calculator and investigate it yourself as well. But I've got this graphed. I'm just going to start this on the standard window. And when I graph this on the standard window, you can see that there's something, a little bit strange going on at x is equal to 0. So I'm going to zoom in a little bit. I'm going to hit zoom and then number 2, and I'm going to zoom in on the origin. And when I zoom in on the origin, again, you can see that this is looking kind of strange around x is equal to 0. And you can actually see if you were to trace on the graph, there's no function value defined at x is equal to 0. I'm going to zoom in again because it's actually not quite as simple as it seems. It's actually much more complicated. The more that I zoom in on x equals 0, the more that you're going to see this graph is actually oscillating up and down, back and forth across the x-axis. So what's happening is the more I zoom in, the closer I get to 0, the more oscillations I have back and forth across that x-axis. And so from the left-hand limit standpoint, there is no left-hand limit because that graph will just oscillate more and more and more the more I zoom in. From the right side, the same thing. I'm just going to see more and more oscillations from the right side. So that's where we're getting that term oscillating discontinuity. I'm going to zoom in one more time just so you can see that it doesn't matter how many times I zoom in. I'm never going to be able to see that this is approaching anything. And in reality, there's no function value defined at 0. And you've also got, those limits that do not exist as you approach 0 from the right and from the left. So that's an example of an oscillating discontinuity. You're typically going to see an oscillating discontinuity when you're seeing something like a sine of 1 over x or a cosine of 1 over x, something where that trig function is going to become undefined. That's going to cause you to have those weird things going on with your graph where you might see an oscillating discontinuity. Okay, so I've got a just quick example here just as a little bit of review. It says redefine this last function to remove the discontinuity. And we had this function x cubed minus 7x minus 6 over x squared minus 9. So just as a little bit of refresher, this is stuff that, is one of those prerequisite skills that I don't think we spend a lot of time on in that Are You Ready for Calculus packet. So I want you to go ahead and work through that problem. So pause the video, work through that, and then when you've got an answer, unpause the video and we'll talk about it. Okay, so here's what you should have come up with. So this is basically doing what was done on the previous page of the notes. So I've got my function, and I apologize, this is a little bit messy, but I've got my function here, and what I'm trying to do is I'm trying to figure out where do I have a removable discontinuity. So it's pretty clear that the denominator, I've got x minus 3, x plus 3, and it's clear that I'm either going to have something going on at 3 or negative 3. So I've either got a hole in the graph or I've got a vertical asymptote at those 2 points. Well, if you factor the numerator, and the way I factored the numerator is just by doing synthetic division. So knowing that either 3 or negative 3 was going to be one of the factors that I wanted to check for in the numerator, it made it a lot easier. I just went through and checked 3 first, found that it did give me a 0 remainder with my synthetic division. So from that, I can see it factors into x minus 3 times x squared plus 3x plus 2. And now what I've got is a situation where I can cancel this out. And essentially what I'm doing is I'm getting rid of that discontinuity at x minus, or at x is equal to 3. And now I know my function is essentially going to behave like x squared plus 3x plus 2 over x plus 3 when I get very, very close to x equals 3. So now I could take the limit of that simplified form of the function, and that would tell me where the hole in the graph is going to occur. So now we can fill in the hole in the graph. I've got my piecewise function g of x defined. Notice the first part of this. This is exactly what we had before. We have that exact same function. We're saying that we're going to basically remove the discontinuity at 3 by saying this is our function when x is not 3. And then this is the value of the function when x is 3, and that would fill in the hole in the graph. Now, there would still be a discontinuity at x equals negative 3 because there's a vertical asymptote. I can't do anything about a vertical asymptote. I'm just stuck with that. But when it's a removable discontinuity, we can rewrite the function so that it becomes continuous. Okay, so let's take a look at this next question. So the next question, it says, find the constant a such that the given function is continuous for all values of x. So when you see problems like this, remember, if we want to think about continuity, we're thinking about the limit value needs to be equal to the function value. So I'm going to give you a minute to pause it, try to figure out what a would have to be, and then we'll talk about the solution for this one. Okay, so here's what you should have come up with for this one. Now, the first thing I'm thinking about is my left-hand limit and my right-hand limit. So my left-hand limit is going to be, you can see where I have x less than 1. So as x is approaching 1 from the left, I'm looking at the rule ax minus 4. So I'm just going to substitute 1 into that to figure out that one-sided limit. And that's where this expression came from that I have here. So this a times 1 minus 4 is like my left-hand limit. 3 times 1 squared is like my right-hand limit. 3 times 1 squared is also the function value. So if I can make that left-hand limit equal to that right-hand limit, I know this is going to be continuous. So now I've just got a simple linear equation that I need to solve. Just solve for a has to be 7. And you could go through and you could test that. You could graph it if you want and see that it's continuous. But the main idea is now the limit value is equal to the function value. So it's not difficult to do once you understand the idea behind it. But like I said before, it's a really common type of question that you'll see, mainly because they want to have an easy way to test whether or not you know that main definition that the limit value has to equal the function value. Okay, so on this next page, we've got just some properties of continuous functions. And the main idea, just as an overall summary, if I have two functions that are continuous and I combine them really in any way, I'm going to end up with a function that is now continuous. Meaning when I say combine them, I mean add them, subtract them, multiply them, divide them, multiply by a constant. The only exception to that is what you see right here, where it says if I divide the functions, I have to make sure that that function in the denominator is not going to be 0. Because if that function in the denominator becomes 0, well, now I'm going to run into a vertical asymptote, and I've created a discontinuity in the graph by that being 0. So that's the only special case. But the main idea is if I have two continuous functions and I combine them, I'm going to end up with a continuous function. Okay, so here's an example of combining some functions. It says, show that y is equal to the absolute value of 2 times the sine of x over x squared plus 2 is continuous. So that's not a function that you probably know very well. And really the idea here is not just to graph it on the calculator. The idea is to think of this as a composite function. So I'm going to say I've got two functions. F of x is equal to the absolute value of x. And I'm going to say g of x is equal to what's inside there, the 2 sine x over x squared plus 2. Okay, so think about the absolute value of x. F of x equals absolute value of x. Is that continuous everywhere? Okay, so you should know that graph. It's got that V shape at the vertex at 0. We know it's defined, so that is a continuous function. Now you can look at g of x. Well, g of x is a little more complicated, but you can break it down into its pieces. Look at the numerator. Is sine a continuous function? Okay, so yes, that one is. We know sine is defined for all values of x. And then look at the denominator. Is there anything in the denominator that would make it 0? So that would make this rational expression undefined. There's nothing that would make it 0. So in the end here, what I can say is f of x is continuous everywhere. And g of x is continuous everywhere. Okay, so therefore, y, which is f of g of x, because remember, our original function was the absolute value of 2 sine x over x squared plus 2. So I'm just doing the composite function. This one is also continuous everywhere. Okay, so fairly simple to do. The main idea is, when you combine these functions together, you're going to end up with a continuous function if the two parts are continuous. All right, so the last thing we have to talk about here is the intermediate value theorem. And I mentioned at the beginning that the two important things that you need to remember out of this. For a function to be continuous at a point, the limit value has to equal the function value. Second part is the intermediate value theorem. So this is the first theorem that we're going to talk about in this class. And there's a few theorems that you have to remember. There is the intermediate value theorem, the mean value theorem, the extreme value theorem, fundamental theorem of calculus. There's a few that we're going to go through, and it's like these are very, very important things you have to know. The big thing to note is you don't really have to know the name of the theorem. You just have to know what the theorem says. And this intermediate value theorem is super easy. And I often refer to this one as the common sense theorem because it's something that you would know without even somebody defining it for you. But this is the mathematical definition that allows you to justify what you're seeing, just through common sense. So what we are looking at here is the graph of a function. And you can see this function is starting over here at x is a, and it's finishing over here at x is b. And we started at f of a, and we finished at f of b. So what the intermediate value theorem says is that if my function starts at f of a and finishes at f of b, in order for me to get from f of a to f of b, I had to cross over every y value or every function value between f of a and f of b to get from one point to the other. And we know that's true because it's obvious here. We crossed over everything between f of a and f of b, that you can just see it and you know that. But what makes it required to be true is the fact that this function is continuous. I can't skip over any values to get from f of a to f of b. So the continuity is the key to the whole thing. If I have a continuous function and I start at some value and I finish at another value, I know I had to cross over every value in between. Okay, so as just kind of the general idea and why this is important to us, we often use this to justify where we have zeros in our function. So for example, if I have a function that starts at -1, and let's say the left endpoint's at -1 and the right endpoint's at, 5. Well, did the function cross over 0 if it went from -1 to 5? And the answer is, if it's continuous, then it had to cross over 0. And so that's really the whole idea of this. So very simple to use. Now, the key to this all is, though, even though you don't have to memorize the name of the intermediate value theorem, you have to memorize what it says. So like I said before, it's important to know what it says. So I'm going to show you here how we can justify when we use this. So this problem says, explain why the function x cubed plus 2x minus 1 must have a 0 in the interval from 0 to 1. Okay, so let's just start with kind of the easy part of this. Let's think about our endpoints. If I plug 0 into that function, it's pretty easy to see I'm going to get -1. if I plug 1 into that function, it's pretty easy to see that I'm going to get 2. So did the function cross over 0? And the answer is yes. Obviously it did, because I went from a negative to a positive. But that is not a mathematical explanation in terms of how do we justify that this actually happened. So really what you're going to need to do in a situation like this is you're going to have to write out a statement. And I'm going to warn you in advance, you're probably going to have to do this either on a quiz or a test. I'm going to require you to go through and write out the details of this type of a statement. Number one, to make sure you know the intermediate value theorem, but number two, because this is very likely to show up on your AP exam as well. And if you don't have the key pieces of information in your statement, then you're going to lose points on your AP exam. And we don't want that to happen when it's something simple like this. We want to make sure that we understand what's important in our writing when we're writing a mathematical explanation. Okay, so you can word this in different ways, but the important part is you've got to have the pieces, and I'll show you the pieces that are important at the end. Okay, so I'm just going to write a statement here. So since f of 0 is -1 and f of 1 is equal to 2, there must be at least one 0 on the interval, let's see, on the interval or in the interval, and our interval 0 to 1, because f of x is continuous everywhere. Okay, so that's the statement. Now, notice that I've got basically exactly what it says within the intermediate value theorem. So I'm going to show you the key pieces to this. So the key pieces here, I've shown that the function went from negative to positive. I also mentioned that there's at least one 0. There could be more than one, but I know there's at least one because it went from a negative to a positive. And the reason I know there's at least one is because this function is continuous. Now, the other part of this that you do need to include is you need to make sure you mention the interval that you're talking about. In this case, because f of x, this cubic function, is continuous everywhere, I mean, the interval, I don't need to restate it again at the end, but it is continuous within that interval 0 to 1. So those are all of the key pieces of information that have to be there. You don't have to phrase it in the exact same way. You can rearrange the sentence however you want. But the important part is show that the function changed sign, mention that there's at least one 0. In this case, we know there's probably only one in that interval, but there's at least one. And then we want to state the interval we're talking about, and we want to say that our function is continuous in that interval. Okay, so not super difficult, but if you have to write that statement out and you don't really know the details of the intermediate value theorem, you're going to leave out something that's important. The number one most important thing in here is the continuity statement, because without the function being continuous, the intermediate value theorem, that's not necessarily true. So once you state continuity, now we know the intermediate value theorem applies. All right, so I've got one more problem for you here, and this is an old AP exam question. So this is an actual multiple choice questions from an AP exam, and I don't remember what year it's from, but it's several years back. And what they want you to do here is they want you to answer this question. So I want you to pause the video, read through the question, and try to answer it. There's really no work involved. This is just completely being done via logic and what we learned in this lesson. So take a minute and solve that one out. Okay, so what you should have found is that the solution here was 0. And again, this is kind of going through what's happening with this. So it says the equation f of x equals 1/2 must have at least 2 solutions in the interval 0 to 2 if k is equal to what? So Think about if I put a 0 here instead of a k. If I put a 0 there, that means from 0 to 1, the function value went from 1 down to 0. So I had to cross over a half. And then from 1 to 2, the function value had to cross over 1/2 because it went from 0 to 2 and it's continuous. So it's pretty obvious. If you're not sure, if that doesn't make sense right away, what you can also do is just plot the points and plot the line that we need to cross, and it becomes a lot more obvious. So the 0.01, I'm just going to estimate where these are, the 0.22, and we're talking about the line y equals 1/2. So that's what we need to cross over. So if I have a point that's above that line, like if I choose something up here, obviously that's not going to work. If I have a point on that line, I'm only potentially going to touch it once. I could touch it more than once, but I'm not guaranteed to touch it twice. But if I put a point down here below the line, like 0, like they mentioned, now I know I had to cross over going down, and then going back up, I had to cross over that 1/2 line. Okay, so that's really everything on continuity. Like I mentioned at the beginning, it's not a difficult concept. It's more a matter of knowing the detail, knowing that the limit value has to equal the function value, and knowing the intermediate value theorem. So work through that assignment, and then next time in class, we'll talk about any questions that you might have after you went through this lesson.